Right, let's look at one or two examples and then we'll leave it at that. So how about the density of some cube? I'm imagining in my head something like a plastic cube. So it looks something like this. And it's a cube, so it's the same length on each side, and let's say 5 centimeters, 5 centimeters, and 5 centimeters. I weigh it on a digital scale, and the digital scale gives me a reading of, let's say 0.20 kilograms, which is 200 grams. So those are my measurements, and okay, I'm making these numbers up, but you should be able to follow what I'm talking about. So let's imagine the cube was measured on a ruler, and it's not a very good ruler. The smallest increment is 1 centimeter. So we've got length 1, which is my 5 centimeters. And if it's an analog ruler, the smallest increment is 1 centimeter, so my uncertainty is half of a centimeter. Well, length 2 will be the same, and so will length 3. There we go. Now let's take a look at the mass. Well, we can see again, not very good scale. Okay, that's the number from my scale. So the mass is measured in here in kilograms, and the smallest increment is 0.01 of a kilogram on my digital scale. So we have 0.2 kilograms plus minus 0.01 kilograms. It's the smallest digit on my digital instrument, so I take that as my absolute uncertainty. Well, to calculate the density, density, let's use that Greek symbol rho, is going to be the mass divided by the volume. And very simply, we have 0.2 kilograms, and the volume is the length 1 times length 2 times length 3. So we have 5 centimeters cubed, 5 times 5 times 5. And putting that into my calculator, please wait, gives us a very small number, 1.6 times 10 to the minus 3 kilograms per centimeter cubed. That's the easy bit. Now I want to know what is the uncertainty in this number, this value of density that I've just calculated. So remember then, step 1, we need the fractional uncertainties. So fractional uncertainty in L1, so 0.5 divided by 5, which is 0.1 there. Now that's also the fractional uncertainty for length 2 and also the fractional uncertainty for length 3. Now what about the fractional uncertainty in my mass? We're going to need that as well. So delta m over m, and we have at the top here 0.01 divided by 0.2. These are not very good instruments. They have very poor accuracy, poor uncertainties I should say, poor precision, but whatever, it's just an example. So there we go, we've got the fractional uncertainties for all our quantities. Now remember, we are now dividing quantities, and the rule is when multiplying or dividing quantities we add the fractional uncertainties. But there is something a little different about this one. Now how did we calculate density? Well, density was mass over volume, but remember this was mass, and on the bottom we had length 1 times length 2 times length 3. So we need to add the fractional uncertainties of all of these quantities. Now, as we've seen up here, the fractional uncertainty in 1 is the same as 2 and 3. So what I actually have, because this quantity is the same as this, which is the same as this, we have 3 times the uncertainty of this. And there's an interesting rule for you, by the way. When you square or cube a quantity, on the bottom we're cubing the length, aren't we? It's L1 times L1 times L1, because they're all the same. You can simply take the uncertainty of one of those measurements and multiply it by the number which you're raising to the power of. If you're squaring it, it's 2 times the uncertainty of that. If it's cubing, it's 3 times that. If it's square rooting, it's half times that, okay? So let's just put in those numbers, and we have here 0.1 plus 3 times 0.05 which is 0.25. Now this is the fractional uncertainty in my density, but we're not done yet because we want the absolute uncertainty in my density. So the fractional and absolute uncertainty of the density divided by, which is the fractional uncertainty of the density is defined as what you see there, the absolute uncertainty of the density divided by the density, and we've just shown that that is 0.25. So rearranging that gives, now I've forgotten what I calculated earlier for the density, so let's go take a look. 1.6 times 10 to the minus 3, which, if my maths is correct, should be 0.4 times 10 to the minus 3. And there's my final value. The density is 1.6 times 10 to the minus 3 kilograms per centimeter cubed, plus minus 0.4 times 10 to the minus 3 kilograms per centimeter cubed. One more little tip for your IA, don't forget to put the units here as well. Okay, the units go there and they go with the uncertainty. There we go.